Welcome to the second lecture of the third week of the course in machine learning. This lecture will be about decision trees. So, let's talk about decision trees. And some general characteristics of this representation. So, actually, decision trees is something that's been developed in decision analysis, where a tree can be used to visually and explicitly represent decision alternatives and decision-making options in various situations. Typically, a decision tree is drawn upside down with its root at the top. Nodes in the decision tree represent features. Edges represent feature values or feature intervals, which and of course the feature values and the feature intervals embody decision options. Leaves represent either discrete values. Typically then these discrete values represent situations or classes. But it can also be that the leaves represent continuous outcomes. So this discrete case, we talk more or less about classification of entities and situations, while in the second case we talk about regression situations. In the decision-making scenario, decision trees are typically used in a purely normative or prescriptive mode. That we can actually set up a tree that is the guide for how to behave. And the decision tree is then simply stipulated. So if you look at a simple example to the right, you say this is a manual for how to act. So you wake up in the morning, you look if it's raining. Okay, if it's raining, if it's not raining, don't do anything. Then, in the other case, you may say, "Oh, is it windy? It's raining, but it's not windy. If it's not windy, I can bring an umbrella." And so on, and so on. So it's a little manual for how to decide. It's a slightly different setting in machine learning, because in machine learning, when we do work with decision trees, we actually want to build up a relevant tree from data sets collected in a domain. So it's not predefined, it's not prescriptive. The tree should be more or less true to the data considered. So the tree challenge here is to design an optimal tree so that the tree makes the best fit of the considered data and has the best predictive performance for new data items. So the interdisciplinary sources of inspiration for this representation, as has already been mentioned, is decision-making theory in economy and business, which have for a long time used simple models of this kind. As has also been said, is that these models are normally defined and they are prescriptive. But there is an interesting parallel, of course, because we will see when we try to build this kind of trees from data sets and with the aim of having a true picture or close to the data set. Of course, we hope that even if a person or some persons just define this tree, the way they do it is indirectly and informally based on earlier experiences from their side. This is the normal case. So at some point, learning takes place. Either it has done informally among the people involved, or we do it formally in the form of machine learning. So the core components and the core problem solving for this representation is as follows. So you construct the tree, you construct it upside down with the root at the top. If you do this manually, you intuitively choose some order of features, and the features you represent as nodes. And from each level, from each node, you branch the tree by looking at the values. So of course the edges represent on every level feature values or feature intervals. And finally, when you come to a leaf, that leaf represents a discrete or continuous outcome. So that's the build-up of the tree. The use of the tree is also straightforward. You start from the tree, the top, and evaluate the values of the features in the given order, eventually up with a leaf with a unique outcome. If we now turn to learning for this representation, which means that we want to build up a decision tree for a realistic domain with many features and many data types. So then we consider two kinds of decision tree analysis. One we can call classification tree analysis, where the leaves are the classes of the categories that we want to define, or regression tree analysis when the leaves are intervals or real numbers or real numbers. The challenge is to design a tree so that this tree optimizes the fit of the considered data items and the predicted performance for still unseen data types. Minimal prediction error is aimed at. And it's not trivial because we may have many features to look at. And it's not crystal clear for most domains which is the most important or discriminatory feature to use first. Because of course the idea is to start building the tree using the features that best discriminates among the data. And there are several approaches that can be combined in addition to learning techniques. So one kind of technique is kind of proactive, which means that at every point we evaluate the whole data set with respect to a potential selection of a feature, and we analyze the discriminatory power of that feature using different kind of approaches. And typically the way we evaluate is by looking if on some kind of information theoretic measures on the whole situation. And there are approaches referred to as information gain based of some entropy concept. There are also an approach called Gini impurity measure. But the purpose in general in all these cases is to judge the discrimination power of the feature. Another kind of measure to take is to first contract the tree, but then at a later stage in the process prune it. And there are of course also different techniques and criteria for what is a good way to prune. A third approach is to actually generate several trees instead of just one in parallel. So this means that through the process, the design process, we generate not just a tree but a forest. And and then further on in the process evaluate which is the most optimal tree within the forest. One criteria that is always important to have in the back of one's head in this matters is the very well known principle called Occam's razor, that of course if there is a choice of structure you should always prefer the simplest choice or the simplest equivalent tree in this case. So if we look at what happens to the data set when we fabricate a preliminary tree, we can observe that what always happens is that if we have a population to start with, so in this simple example we have like 14 data items in the root, and then we make the first split. We use one feature and we split up in three possibilities, which are the values of that feature. So then what happens is that by doing that, we also in a way split the data set or the data set into three boxes. And then in the second step, when we make the second split using some other feature, we make a split again. And of course, it should always hold that at every step in the split, the sum of the items in the boxes created should sum up to the original data set, which was 14. So as you see here, for the first split, we divide up in three boxes, and when we take the second step, we don't go further with the third option. We go only split further the two first options, but altogether the five resulting leaves in that case partitions the data set as a whole. Another perspective on what's going on in this process is to compare a preliminary tree with some other graphical depiction of the feature space. So if we, in this very simple case, have two features, and we in a way split with respect to one breaking point for each of these. This example illustrates how the three constructed partitions a two-dimensional depiction of this little feature set. So as you can see here, there is 1/4 of the area that represents one option, and 3/4 of the area that represents the other option or outcome. So I will end this lecture by showing you a few examples. So the intention with the first example to show you like a complete picture where you get a whole data set with a number of data items and then a corresponding tree. Whether that tree is optimal, we're not going to discuss at this point. We will come back to those issues next week when we look into a variety of algorithms that has been designed for this kind of problem. So this example relates to the analysis of election outcomes in the US. Essentially, the features in this example are the outcomes in the various states. So this means that the ordering of features is based on the importance of those outcomes for the final results. And as you see, this has been done here in such a way that the tree is reasonably well behaved, in the sense that one of the alternatives, what is depicted as blue here, are kind of more dense to the left, and the other alternative, the red outcomes, are sorted to the right. So I give you two more examples here. I won't say much about them, just a few comments. The left one is a classification example, and the right one is a regression example. So in the left one, the classification is essentially in two outcomes. A child gets a Christmas gift, or a child doesn't get a Christmas gift. Those are the two only outcomes on this. And of course, as you see, the outcome can depend on certain behaviors of the child. I have no further comments on the regression T example, but can you see here how what was illustrated earlier, that the population of the data items in the data set are on every level distributed among the leaf nodes at that point. So this was the end of this lecture. Thanks for your attention. The next lecture will be on the topic of Bayesian belief networks. Thank you. Goodbye.